Data engineers face a constant structural tension, extracting real-time operational data into an analytical environment without breaking the production system. Historically, teams solve this using point-to-point streaming pipelines, relying on stateful infrastructure like Debezium and Kafka. But directly coupling a high-throughput transactional database to an analytical destination creates a highly brittle architecture. As message volumes spike, the rigid pipeline struggles to balance the load. If the destination data warehouse experiences any downtime or maintenance, the pipeline has nowhere to deliver the data. It drops messages, resulting in permanent data loss. Achieving true real-time integration requires abandoning that direct connection in favor of a fully decoupled asynchronous architecture. We can construct a modern alternative, a 3-tier decoupled real-time change data capture, or CDC, pipeline. For this architecture, we will use Estuary for the capture layer, DuckLake for open intermediate storage, and MotherDuck as our compute engine. To understand exactly how this solves the latency and durability problems, we are going to track a single operational record from a database's binary log all the way through to a sub-second analytical query. Tracing this precise path reveals the inherent engineering trade-offs between utilizing open table formats and prioritizing proprietary query speed. We begin building the architecture at the source with the capture connector phase. Instead of querying the database directly, this connector reads the Postgres write-ahead log, the WAL, identifying every microtransaction the moment it occurs. There is a strict architectural rule here. This connector is entirely responsible for extraction. It does not push data to any final destination. Instead, it feeds the decoupling layer, dropping the extracted data into a user-controlled S3 bucket as raw JSON documents. These documents contain the raw data alongside crucial operation metadata, specifically flags like U for an update and C for a created record. This creates immediate fault tolerance. If the downstream warehouse crashes, the operational data simply continues to pool safely in this S3 bucket. This intermediate storage also allows engineers to execute multi-destination backfills. You can load that same data into Snowflake or Kafka simultaneously, without ever requerying or stressing the original Postgres database. Injecting a layer of intermediate blob storage turns CDC from a fragile real-time stream into a durable, highly replayable asset. Once the data is safe in S3, we introduce the final pipeline node, the materialization connector. This connector processes the raw JSON documents and writes them into DuckLake, an open table format built on Parquet files. Here, we hit a major architectural problem with traditional open table formats, like Iceberg. They typically store their structural metadata as JSON or Avro files directly alongside the data in that same blob storage. Blob storage is not optimized for rapid, small read-write operations. Managing metadata there causes severe latency bottlenecks during complex transactions. DuckLake's structural innovation is to extract the metadata layer entirely out of the blob storage. By placing that metadata into a high-speed relational database, DuckLake dramatically accelerates transaction speeds and lookups, while keeping the raw underlying data fully open. It solves the primary data lake bottleneck by treating metadata as an operational database problem, rather than a file storage problem. With the data materialized, we introduce MotherDuck as the analytical compute engine sitting on top of DuckLake. When MotherDuck first reaches into the remote S3 Parquet files, it encounters a cold start query, inheriting the natural latency of cloud storage. However, that initial cold query is actively hydrating MotherDuck's internal caching layer. Subsequent queries bypass S3 entirely. They hit only the fully populated local cache. This enables a feature called Instant SQL. Because the data is cached, data engineers receive sub-second query feedback at the literal speed of typing, validating logic without waiting on remote network calls. Aggressive caching is the required bridge to negate the latency of remote cloud storage during active development. Now that the pipeline is flowing seamlessly, we have to confront the absolute physical limitations of data engineering. You must explicitly choose between maximum openness and maximum performance. You cannot have both simultaneously. Open formats like DuckLake's Parquet intentionally sacrifice absolute read speed to guarantee cross-platform interoperability. This split-screen chart illustrates the alternative. Proprietary storage formats, like MotherDuck's native storage, are engineered exclusively for read and write throughput. The right side shows a 5x to 10x read speed advantage over the open Parquet baseline on the left. This speed differential exists at the physical I/O layer. The proprietary format makes specific trade-offs regarding compression and data locality that an open format simply cannot make without breaking its universal compatibility. Because no single storage format optimizes for both openness and speed, architects must split their infrastructure based on the data's immediate purpose. We apply this law of physics to a production medallion architecture, dividing the pipeline into bronze, silver, and gold layers. The bronze and silver layers utilize Estuary and DuckLake. This prioritizes massive scale, cheap S3 storage, and open interoperability for the raw incoming data. Transitioning to the gold layer requires heavy, complex aggregations and transformations on that massive body of silver data. We handle those heavy transformations by spinning up massive compute clusters, like MotherDuck's Giga instances, which are specifically designed to churn through data lake scale operations. The results, the final gold analytical tables, are then materialized directly into MotherDuck's native storage, rather than written back out to Parquet. By putting the final layer in a proprietary format, downstream analytics and business intelligence dashboards receive that maximum 10x query performance. Modern data architecture relies on ruthlessly decoupling your capture, storage, and compute layers to ensure maximum efficiency. You exploit the specific mathematical advantages of each, rather than forcing one tool to do everything.